This talk will probably be too mathematical for some of you, but I'm a person who is a really good fan of math. So this is a story of how I found e to 5 million digits, starting from scratch. So the motivation. To start with, the problem itself is very useless. No more than 14 digits are used, but it is a very challenging problem because you have to deal with limited amount of memory, especially that sometimes you have to go for a billion digits, which is almost 1 terabyte of data. And try fitting that on a RAM. It is very rewarding emotionally. After working on it for almost a year, I was very happy. And a bit of improvement can save a lot of time. And with enough time and patience, you might find a record-breaking number. Now, why E, not phi or pi? Pi is too mainstream, but pi is used in baby geometry. E is part of the most beautiful mathematical equation, ei pi plus 1 is 0, and you might find your name somewhere encoded in there. I haven't found mine, but if your name is Remy, then it says somewhere in there. And E is found to 1 billion digits as opposed to 10 billion. And this is a list of funny and ridiculous ways. Yeah, it's actually trillion. This is a typo, sorry. Okay, now, how do we start by finding these digits? We consult our calculus books or the literature, and we find the limit or the Taylor series. These are very good. But which one do we pick? We will choose the Taylor series because it's easier to work around with it. It's easier to optimize, and we can use the binary splitting because it works on hypergeometric series, and we can use the caching and dynamic programming to make it faster. And for this infinity, we can work around how exactly we want this infinity to be. Now, how do we find this infinity? And remember that we're not after an infinite amount of precision. We're just after a big amount of precision. If we use the error estimation theorem in calculus, or more intuitively, we need to stop summing after the numbers stop changing the digits pre the pth digit. Now, this is the math that we do, and we get that the number of precisions is the ceiling of log of n factorial, where n is the number of iterations we do. The iterations are these infinities we deal in the Taylor series. For example, for 1 million iterations, we get 5.5 correct digits in E. Okay. Now we need to optimize this Taylor series because we can't really use it. Steve Wozniak, the co-founder of Apple, actually found 116,000 digits, and he broke the world record back then on his own personal computer. And he wrote a paper about it called The Impossible Dream, Computing E to 116,000 Places with a Personal Computer. And the link of the paper is here. You can, Samer will probably provide the slide later. The way he did it is that he used an infinite division rather than an infinite sum. And this is how it looks, where n is probably the infinity that we're after. Now, why is this form better? Mainly because we reduce the amount of operations from 3 operations to 2 operations. And the first one takes constant time to complete, while the second is p time to complete. All in all, it takes n times p, which is n squared log n of time, as opposed to n cubed log squared of n, and if we use the infinite sum. Now, we need to do that. It's time for implementation. Should we use Java's big integer library or GNU MP? No, you should not. Multiple precision libraries tend to convert, and they do a lot of checking before every single computation. In our case, we know that we don't have, for example, negative numbers. So why check if we have a negative number? As well, it's more fun and challenging, and you can brag about it to your professors, and they get exempted from the C++ course. This is an example on how horrible Java was as opposed to something that I built. This here is Java, and this is an optimized version of my MP library. And these are all past instances of my multiple precision library. Now, how do we represent these 10 to the power 5 million digits? Suppose we have a 16-bit machine and we want to represent 1, 2, 3, 4, 5, 6. We can do that, and we can store it as an array of strings, which is a string, which is an array of characters. But then we will have to deal with converting the characters to integers back and forth. What we could do is that we can store it as an array of every single digit, and I will call it as one block. Or we can store it as 4 blocks, where we concatenate every 4 characters, 4 digits together, and reduce the size of the array. Since doing computation on single one of them is equal to doing on 4 of them, we save block times of time. So if I use 4 blocks, the program will run 4 times faster. Now, how do we represent the floating points? In my multiple precision library, I don't. What I do is that I find e times 10 to the power p, and I take the floor of it, which becomes later on an integer. And then when I want to see the number, I just take the dot and put it after the first digit. And then for example, if I chose p is equal to 6, I will get 27182, and then I'll put the dot here, which will be e. Now, how to add one? In my pseudocode, I like to use 1 as opposed to 0 as indexing. So adding 1 is very trivial. We just take the first 1, and then we add to it the 10 to the power blocks minus 1. Unfortunately, I don't have time to explain in details how these work and why they work. But if you want to know, my email is down there. And how do we divide? I simply use the algorithm that we took in 10th grade, probably, or in the 1st grade, and just apply the 2 numbers, where we loop on single one, and we divide, and we get the mod and add it to the other one. And if you put everything together, we get the final product, which is very simple. We get the precision, which is log of n factorial, where n is the amount of iterations we need. We create the array in which we want to hold the numbers. We add 1 to it, and we do the infinite division, and we return the data. Now, how do we check if our digits are correct after running them for 14 hours, or for, in case of pi, for a year? How do we check if they work? In my case, I can compute 1 over e, which is in the Taylor series minus 1 to the n over n factorial, and then flip it around and compare it to the result I got. If it's equal, then I got e. Or I can use a trusted software, or I can use these sources provided by NASA, for example, for 2 million digits, 10 million digits, and the current record holder provided the 500 billion digits for e, and snippets of them. And then there's a torrent, which doesn't really work anymore, which has all of the 500 billion digits. I can still use future improvements if I want to make it run a lot faster. I can use binary splitting, which works this way. You can read about it. It's very simple. And I can use a fast Fourier transform to do the multiplication and the division. And I can parallelize the algorithms and as well use the GPUs. Alexander E is currently the world record holder for every single constant you might think of. Square root of 2, e, pi, phi, log 2, log 10, zeta 3, another Euler constant. And he uses a program he wrote called Y-Cruncher, and his homemade computers, and he finds these numbers. He did release a code on GitHub, which is called the MiniPy, that finds pi and e in n log cube of n, which is 100 times slower than the actual program. This is it for my talk, and wish me luck if I want to work to break the record. And if you want to contact me, I'm on IRC and my email. Thank you.